Hello, our next speaker is Nikola Obrenovic from Bioscience Institute. So he will speak about applications of OR in transportation. So any transportation system requires detailed planning and good decision making in order to function properly. So decisions need to be made at all planning levels. To support making optimal decisions, mathematical models are built and solved by different methodologies of mathematical optimization and operational research. So in this talk, he will be presenting three optimizational problems in the field of transportation, spanning all decision levels and proposed solution methodologies. So let's start, Nikola. Thank you.
Good morning, ladies and gentlemen. My name is Nikola Obrenovic. I'm a senior researcher at the Bioscience Institute at the University of Novi Sad. Today, I will be talking about the applications of operations research in the field of transportations. In particular, I will be talking about the three projects which I worked on while I was a postdoctoral researcher at the École Polytechnique Fédérale de Lausanne in Switzerland. So the first project was about designing a network of marshalling and shunting yards for the national cargo railway company in Switzerland named SBB Cargo. And this project was done with the experts from their side. So to give a short introduction, what are marshalling and shunting yards are. So those are the bundling points where the train company assembles commodities which are coming from the close-by origins. They assemble those commodities into a single train compositions, which is then like that transported to a marshalling or shunting yards, which is close to their final destinations. There the commodities are disassembled from the train composition and sent via smaller but direct trains to their final destinations. And the main difference between the marshalling and shunting yards is in their size. So the marshalling yards are larger, have a bigger capacity, but also they cost more. So the operating and maintaining marshalling yards cost more compared to the shunting yards. So in the current SBB cargo network, we have 5 marshalling yards, a few of them on the borders and 2 of them within the Switzerland, and we have approximately 70 shunting yards, 50 of which we were able to change, relocate, close, or even close down. And the solution of this project was supposed to provide the optimal number of locations of marshalling and shunting yards throughout the Switzerland, then the set of the trains to be used for the commodity transportations, and finally assignment of the commodities to those trains. So as in any optimization problem, we started by its definition. So we realized that this problem is a combination of a hub location multi-commodity network design problems, which are well-known problems in the transportation, well-known optimization problems. So we combined these two problems, we extended it for the purpose of this particular case. So first we defined the objective functions, which consists of the costs of commodity transportation. Then we have the locomotive and staff costs, and finally we have the commodity shunting costs, which actually happen whenever a commodity is bundled or unbundled from a train. So our purpose was to actually find a solution which minimizes these costs. We used the existing constraints from the 2 named problems, and also we added some additional constraints which are specific to this particular task. So we had a constraint which says that a node in the network can be either a regular station, shunting yard, or marshalling yard. Then we added different constraints for the train modeling, such as commodity assignment constraints, then flow conservation constraints for commodities, which guarantee that each commodity starts at its origin and ends in its destination, capacity constraints. Train capacity constraints. Because this problem size is quite big, we are unable to solve it to find the exact optimal solution. So we needed to opt for a heuristic algorithm which in this case was built to be composed of 4 stages. So first stage was about locating and sizing the yards, the yards within the SBB cargo network. We basically here developed two heuristic algorithms which are based on two different meta heuristics. So the first one was adaptive large neighborhood search, and the second one was variable neighborhood search. And both those meta heuristics use network change operators to explore the huge search space of all possible states of the cargo network. So these operators were either relocating the marshalling yards, or opening new marshalling yards, or turning a marshalling yard into a shunting yard and shunting yard into a marshalling yard, changing the size of the shunting yards, or closing down and opening new shunting yards. Then the second stage of the algorithm was creating some initial trains on very important tracks. We needed to do that is basically because tracks are capacitated with, so they have limited capacity, and we needed to reserve the space on those tracks for these important trains. And in order to prevent a situation like this, that some direct train from between two regular stations to take some of the capacity, and basically this allows these important trains to be run. And then the next stage was assigning of the commodities to the trains. So for each commodity, we select the path which is the cheapest, basically a set of trains which form the cheapest but available path. And then if we cannot find any such path, then this stage of the algorithm basically adds the trains, but only where it is really necessary. And the final stage of the algorithm is now trying to further reduce the number of the used trains by using another heuristic based on the variable neighborhood search. So we try to reduce the number of trains which are either running between two regular stations or between two shunting yards, and if needed, we increase the number of the trains between the marshalling yards or between the shunting and marshalling yards. So we tested these two algorithms with two strategies. S1 allowed the increase of marshalling yards, and here the algorithm based on variable neighborhood search found the best solution, which resulted in cost reduction of around 10%. Strategy 2 was to actually limit the number of marshalling yards to the current one. And with this strategy, the best solution was found by adaptive large neighborhood search, and it resulted in the reduction of operating costs for the every cargo for 16%. Also, what we concluded from these results is that locomotive and personnel costs are dominant over weight-dependent commodity transportation costs. So this, at the end, meant that in the final solution, less locomotives, like basically less trains, so also less locomotives and less staff was used to run those trains, but the commodities were traveling for a bit longer time than in the current state of the SBB cargo. So the overall conclusion is that we were successful in building an algorithm which found a network state which actually resulted in the transportation cost results. We also discovered that we need to further extend this model for to be more realistic by adding the costs of maintenance and opening of the marshalling and shunting yard. But at this point in the project, that was not of interest for SBB cargo, so we did not include it in this particular analysis. Another identified future research direction was actually to build an algorithm for daily cargo management, which would include train routing, train allocation, staff allocation, and also demand prediction. So the second project which I worked on was to build a holistic decision-making frameworks for vehicle sharing systems. And what are those systems? So in these systems, a system user can actually take a vehicle from somewhere in the street, which either can be just anywhere in the street or in specifically designed stations of those systems, to use it for a certain amount of time and then only pay for as much as he or she used it. There are various configurations of these systems. They can be either return way or return one way or return trip systems. In return trip systems, the user must return the vehicle from the location it took it. He or she took it. So in one-way systems, the vehicle can be left in any designated place anywhere in the specified area. Station-based systems has, as I said, marked limited stations with limited capacities, while free-floating systems, you can take the car or any other type of vehicle anywhere, wherever you find it in a city or a larger area, and return it to anywhere, to any allowed parking spot in the same area. Then, regarding the pricing of the usages in the fixed pricing systems, the user only pays by the kilometer which is driven, or by the time the vehicle was taken. In dynamic pricing systems, the price is determined also based on the actual state of the system. So if a user takes a vehicle from a low demand location and drives it to a high demand location, he or she will pay less than vice versa. So, and state of the art regarding the systems showed us that basically most of the challenges are addressed individually and neglecting the influence of the other decisions. Most addressed challenges are system imbalance resolution. So basically, in the systems, in the one-way systems, where we have a tendency that the vehicles are accumulated in one place with low demand, and we have a lack of vehicles in the places of high demand. So we need somehow to rebalance the system to put back the vehicles from these low demand locations into the high demand location. And the two other topics which were quite often addressed were demand estimation and determining of those dynamic prices. However, we saw that there is a lack of a holistic solution approach, which would consider as many as possible problems and also take into account the influences of the decisions made. So we defined a decision-making framework which spans all three planning levels. So strategic planning level, tactical planning level, and operational planning level. So we tried to actually sort the problems appearing at these levels to be either the supply side or demand side problems, and we also tried to identify as many as possible influences between the decisions made at one higher planning level to the models and how the decisions are made in the lower planning level. And by building this framework, we identified several research gaps which still need to be tackled. So first of those open questions is actually how much valuable is the demand model, how much additional value it brings to the system. Also, most of the literature consists of the works about bicycle sharing systems or car sharing systems, while on the other hand, we have new types of vehicles introduced, and we need to see how of these existing methodologies are actually applicable to the new vehicle types. So for the first question, we built a simulation-based optimization framework, which needs to help us analyze the system operations in two marginal cases. So first one is where we suppose that we know the perfect forecast for the tomorrow's demand, and then we relocate the vehicles based on this perfect forecast. In the second case, we don't know anything about the tomorrow's demand, and we are just rebalancing the system each night to the same initial state every day. And with that, we want to compare the trade-off between the lost demand and rebalancing costs in these two cases. So as a case study, we took the bicycle sharing system of Lausanne with its real stations, and we simulated the demand. So, and we found that when we know the demand in advance, we are able basically with the appropriate rebalancing operations to actually come to zero loss demand. So basically, we are able to serve all customers. On the other hand, rebalancing costs increase when we know the demand and we are trying to reach the demand. But on the other hand, this increase is less compared to the lost customers. So what we made in this work is basically what we first built this general framework, which helped us reveal open search questions, and then we focused on first of them. We selected first of them, and which was to quantify the value of demand models, which we managed to do. So the next step is actually to try to apply this framework to a new type of vehicles. Those are light electric vehicles built by a company Enu from Switzerland. They are already operating a vehicle sharing system of their own. And what is specific about these vehicles is that they are smaller than cars, but larger than bikes. So none of the methodology existing can be really directly applied to the management of this vehicle sharing systems. But we want to our framework, we want to identify what can be applied and what needs to be developed new. And finally, the last project was dealing with the railway disruption management in railway systems. So basically, disruptions can happen depending on can be caused from some bad weather conditions, from terrorist attacks, for accidents, and so forth. And in this situation, the goal of the railway operator is basically to provide a new timetable which will cost as little as possible, but be able to serve as many as possible passengers. So the whole procedure is called the recovery problem, and it consists of these three stages. So first is the timetable rescheduling, basically building this disposition timetable, then allocating the rolling stock, and finally assignment of the staff to those new trains. So we in this project were focusing on the first stage of timetable rescheduling. So what we allowed and what is usually allowed in these situations as a recovery decision is either to modify the rolling stock, to delay the trains, to reorder the trains, to reroute the trains, or even to cancel or partially cancel the trains, to include emergency trains or emergency buses, to create additional stops, to add to skip stops or short-term the trains. So again, we built a multi-objective optimization problem to solve this issue, and this problem had the following objectives. So we want to minimize the passenger inconvenience, that is to provide as good as possible service in the new situations to our passengers. Also, we want to minimize the operational costs. And finally, we want to minimize the deviation from the undisrupted timetables. And this last objective is very important, because when the cause of the disruption is removed, we need to be able to, as quickly as possible, return to the regular operations. So again, the problem was a real network of Switzerland, since of very large size. So we had again to use the meta-heuristic approach. which we based on the adaptive large neighborhood search, and the neighborhood change operators, which were inspired from the real life recovery strategies I mentioned earlier, with an addition of emergency buses. So we added another one, a new recovery strategy, which allowed railway operator to introduce emergency buses. And with this meta heuristics, those neighborhood operators compete, and basically the ones which bring better solutions are selected more often. In that way, the search space is sold. So what we were able to do next is the Pareto analysis, which revealed that we can actually provide a very good disposition timetables by only little increase of the operational cost. For example, here, so very small increase in operational cost gives us a very small decrease in passenger satisfaction, and we are able to provide a good service to our clients, to our passengers. So and yes, the higher the deviation from the disrupt times, what we also learned from this exercise is that the higher deviation from the undisrupted timetable does not necessarily create a better timetable in terms of passenger satisfaction and operational cost. So thank you very much for your attention.